All right, so we're live. Okay. Well, thanks everyone for joining and welcome to another TCS Plus talk. And here we're very happy to have Steve Hanneke, who will tell us about a theory of universal learning. And before we begin, let me just thank the rest of the organizers, who include Clement Kanan and India Day, Sumega Garg, Gautam Kamath, Ilya Rajenstein, Oded Regev, Salil Shram, and Thomas Fidik. As well as let me say that in 2 weeks from now, we'll have another talk, Avishai Tal from UC Berkeley. He'll be giving a talk about junta distance approximation. But I'll give the floor to Steve. I will say, please feel free to unmute yourself and ask any questions throughout the talk. The talk is being recorded and we'll post it on our website later. And I want to encourage everyone to keep their camera on to give Steve some visual feedback. But all right, that's all. Steve, please take it away.
Okay, thank you. Yeah, thanks for inviting me. I'm happy to be speaking with you today. So I'll be presenting some recent joint work with Olivier Bousquet, Shai Moran, Ramon Van Hendel, and Amir Yudayev. This is going to appear at Stock 2021. Right, as we all know by now, machine learning is becoming increasingly important in all of our lives, and the field of machine learning it's in a period of rapid development. And as the field develops, a key feature of learning algorithms to understand is their ability to generalize beyond their training data. So the learned classifier predicts accurately not just on the training set, but also future examples as well. And these kinds of generalization guarantees are important, partly because they give quantitative guarantees on how much data is needed, but also just partly because they motivate algorithm design. So in other words, we want to design learning algorithms that provably generalize well. And this gives us a criterion for theoretically comparing different learning algorithms in a mathematically principled way. The classical theoretical framework for studying generalization is the PAC model. However, as we'll see, there are important aspects of generalization that are not captured or described well by the PAC model. Right, what we'll discuss here instead is an alternative framework to the PAC model, where specifically we'll study something called universal rates. So for instance, what we'll see is in this universal rates framework, sometimes it's possible to get even an exponential convergence rate for the error rates, while in the PAC model, you would never predict better than a 1/n rate. And then plus once we can express these exponential rates, then of course we want to design new learning algorithms that fully exploit that possibility. And in addition, this will also give rise to just a rich mathematical landscape in a few different senses. You know, in the PAC model, you get a nearly optimal rate for even simple learning algorithms, just sort of minimize the loss on the training data. But here, what we'll see is to get optimal universal rates, you actually need, it's sort of a more interesting algorithmic problem. And then also in the process, we'll give rise to some really beautiful combinatorial structures involved in characterizing the optimal rates. So that'll come up later. Okay. So I'll start by presenting this, the classical PAC model. We'll then talk about the distinction between uniform and universal rates. And then the main result of the paper is a complete characterization of the optimal universal rates. We'll also we'll dig into the sort of the two fundamental cases that come up, exponential rates and linear rates, and define some corresponding structures, give examples, and outline the main ideas behind the algorithms and proofs. I've pruned this down from like about an hour and a half talk. I'm not sure if I pruned enough, so we might only get partway through the linear rates part, but that's okay. I think the exponential rates really reveal a lot of the interesting structure already. Okay. So Right. Let me begin by introducing the idea that a learning problem is a distribution on XY pairs. So where X is in some space and Y is a binary label. So for instance, the space X might be, let's say, all possible images, and the marginal distribution on X might be, let's say, all images that are uploaded to Yelp, like past, present, and future. And say maybe the label is, let's say, like 1 interpreted as that it's a hot dog, and 0 is not hot dog. Okay, so then we also have a notion of a learning algorithm. This is just, it takes as input a data set, we call it a training set, and we think of that as being sampled from the distribution, and then it outputs a classifier. That's just a function mapping X to Y. And we're interested not just in fitting the sample well, but also generalizing to the rest of the distribution. So in other words, we want to have good prediction accuracy on future samples from the distribution. And quantitatively, we define that as the error rate. That's the probability of making a mistake on a fresh sample XY from the distribution P. Now, for this to be possible, to get a low error rate, well, we'll need some kind of assumption. So for this, we introduce this notion of a concept class. And this is just a set of classifiers. So for instance, that could be all of the neural network classifiers with a given architecture. And then for whatever classifiers are in the class, we'll make this assumption that the distribution P is realizable with respect to the class, just meaning that there are classifiers in the class that achieve low error rate, or error rates close to 0. That's an assumption that we'll make throughout the paper and throughout the talk. I should mention all indications are that you could express these results in a sort of agnostic form also, but we'll stick to this assumption for simplicity. Okay. Good. So, right, in this work, we're going to be interested in bounding the expected error rate and the rate of convergence of that. Now, the classical theory would focus on what's called a minimax analysis, or uniform rates, or we also call that the PAC model. That stands for probably approximately correct. And right, so there's a very clean and concise statement of the optimal rate in the PAC model. It says that for the optimal PAC learning algorithm, in the worst case over all realizable distributions, its expected error rate is proportional to like 1 over the sample size times a complexity measure called the VC dimension, named after Vapnik and Chervonenkis, who are the fathers of this whole field. This is called a uniform rate because it gives a risk bound that holds simultaneously for all realizable distributions. Now, for the purpose of this talk, it's not too important to know the VC dimension, but yeah, just based on this result, we can see there's a fundamental dichotomy between in PAC learning. So if the VC dimension is finite, the optimal rate is like 1 over n, and we'll say it's learnable. And otherwise, if the VC dimension is infinite, then the error bound doesn't converge, and we usually say it's not learnable. So that's a nice simple picture of generalization in the PAC model. But yeah, it turns out these uniform rates aren't really giving the bigger picture of generalization. It's really missing a lot. So like one thing that's been observed empirically is that sometimes learning algorithms are actually getting faster than 1 over n rates, even exponential sometimes. So that's not really captured by this uniform rate theory. And then another thing that's missing is that even with infinite VC dimension, there are algorithms that have expected error rates converging to 0. So in fact, there's a property called universal consistency, where even when the concept class is the set of all measurable functions, some learning algorithms still have expected error converging to 0, for all realizable distributions. So for instance, the nearest neighbor classifier satisfies this in finite dimensional metric spaces. Okay, so yeah, let me now try to make that distinction a little bit further graphically before we get into exactly stating it formally. So a very common type of figure that's included in machine learning papers is what's sort of cutely called a learning curve. So basically you plot the expected error rate of some learning algorithm as a function of the size of the training data set. So here are some examples. These are from a classic paper of Ng and Jordan. For our purposes, it's not too important what these learning algorithms are, but you can see the idea. These are informative. These curves are informative. Like maybe one algorithm is better for small data sets, and then another one overtakes it in the long run. So you see this in a lot of papers. And a key point I want to emphasize is that each plot is for a single learning problem, right? And so a single distribution, right? So then we can ask questions about these types of plots. So we could ask, like, what's the shape of the curve? What's the rate at which it approaches zero, or whatever limit it approaches, but let's say zero. We can ask, is there an optimal rate that a learning algorithm can guarantee all its learning curves converge at? Right, and in particular, we'll see sometimes learning curves converge exponentially fast. And right, observing that this is a possibility, we'll of course then want to design learning algorithms that fully exploit that possibility. Right, so just to really show this distinction, let's have a look at these figures again and focus on this the solid curve in each plot. So that's some particular algorithm. And if we pick a particular sample size, let's say like 15, we can see this, the top right learning problem says that the corresponding error rate is about like 0.28, and that's the worst out of all of these plots for that sample size. But if we look at a different sample size, let's say like 90, then actually the learning problem in the bottom left is the one that has the highest value. So it's some totally different unrelated learning problem, right? So the point I'm getting at is that the classic theory studies these uniform rates, which corresponds to the rate of the pointwise max over all the learning problems. Right, so if you have enough learning problems, the curve of the pointwise max can actually have a very different shape than the individual learning curves. So like even if each individual learning problem has a learning curve converging very quickly, it could still happen that the pointwise max converges more slowly. So in fact, if you had an infinite number of learning problems, even if every individual learning curve converges, say, exponentially fast, it can happen that the uniform rate, the pointwise max, converges, say, at a 1/n rate, or maybe doesn't even converge at all. Okay, so that's sort of the high-level idea of the distinction between universal and uniform rates. To formalize all this, let's again recall a learning problem is a distribution P. So while the uniform rate would study the convergence rate of the max expected error rate, what we'll study here is what rate the expected error converges for all distributions P. To make that totally formal, we'll say a concept class H is learnable at rate R if there is an algorithm such that for all realizable distributions, there exist constants which may depend on the distribution, such that the expected error rate is bounded by constant times R of constant times N. Okay, hopefully that's clear. And given this definition, what we find in this work is there's actually a fundamental trichotomy of optimal rates. So specifically what we can show is for every class, one of these must hold. H can be learnable at an exponential rate, but not faster. H can be learnable at a 1/n rate, but not faster. Or H can require arbitrarily slow rates, meaning that there's no rate R that satisfies that definition. And then we'll also give a complete characterization of which classes fit into which categories.
I have a question actually.
Yes.
So I'm trying to understand how this differs from the pack learning. So if one difference that these constants could depend on the distribution, while maybe there you don't want them to depend on the distribution?
That's right, yeah. So if we were taking the max over distributions, then you couldn't have any constants that depend on the distribution. Whereas here, we want the rate for each distribution. And so those constants could depend on the distribution. Yeah, that's the real main distinction. Good. Okay, so that's that's the main results, what we'll be talking about. And I'll just maybe go through a sort of a warm-up example before we jump into the more abstract discussion. So let's suppose this, in this simple example, suppose we have only 2 points in the space. Okay, there's x0 and x1. And the class H is just 2 classifiers, H0 and H1. And let's say they agree on x0 and they disagree on x1. Here's a simple algorithm. So if any of the n training examples has its xi at the little x1 point, output whichever the 2 classifiers is correct on the point. Otherwise, it doesn't matter, just output either of the classifiers. So then I claim this algorithm actually learns at an exponential rate. So there's a trivial case. If there's no mass on x1, the error rate's already 0, so it's sort of a trivial case. Otherwise, let's say it has non-zero mass there. So then we notice if indeed one of the training points is at x1, then the error rate is 0 in that case too, because only one of the classifiers survived. That must be the good one. So the probability this doesn't happen is like 1 minus the probability at x1 raised to the n. That's like e to the minus probability at x1 times n. And that's an exponential rate. So h is learnable at an exponential rate. Yeah, it's not hard to see that this would also extend to any finite concept class. Essentially, there would be some finite number of types of points, and if you see them one of each type in the data, then all the classifiers correct on those would have error rate 0. So in fact, any finite class is also learnable at an exponential rate. Now things get much more interesting for infinite classes, but the key feature that's going to carry throughout all of the exponential rates discussion is that at some point the algorithm is finished, right? At some point it has 0 error rate. After some finite number of examples, it's already has 0 error rate. And then sometimes we'll have to do a little bit of some tricks in order to make that to convert that into an exponential rate, but that's the key feature that we're going to be focusing on.
Hi, I have a question.
Yes.
Yeah, so it's related a bit to the no free lunch theorem. I'm trying to kind of wrap my head about what's happening. And one thing here is that, again, these constant could be exponentially big into the description length of the input and anything, right? So even though, yes, you will learn in finite time, it could take the age of the universe, right? If the constant is big enough.
Yeah, so you're saying that essentially this exponential curve could be pretty bad for a long time and then start getting really good.
Yeah, because
Yes.
C depends on distribution P. So I could find some distribution. If the finite set, for example, is a big set, it could take a long time.
That's right. Yeah. So and one thing we can do is guarantee simultaneously to be uniformly have optimal uniform rate and optimal universal rate, and that sort of in some cases that will address what you're talking about, but in other cases it won't and necessarily can't. Right? There are these no free lunch theorems, like you said, If you have classes with infinite VC dimension, there will be some distributions where you have to wait a long time before whatever rate becomes a good guarantee on the error. Yep.
Thanks.
Okay. So that was sort of a warm-up example. Moving on to the general case, what we find is whether or not a given class H is learnable at an exponential rate is actually completely determined by whether or not a particular simple combinatorial structure can be witnessed by classifiers in the class. Specifically, this is something called the Littlestone tree. So I'll try to define it clearly just using the picture here. So imagine there's some collection of points indexed by finite binary vectors, and we can organize them into a tree, a binary tree, just using the prefixes. So like the root is x sub empty vector. Its left child is x sub 0. Its right child is x sub 1. Left child of x sub 1 is the left child is x1 0. The right child is x1 1. So just like what's in the picture, and so on. And then we'll also label the edges. So the edge will always be labeled, if it's a left branch, it will be labeled the parent's X and then a 0 label. So it's a labeled XY pair. And if it's a right branch, then it will be the parent's X and a 1 label. Okay. And so that's the type of tree. So imagine we have such a set of X's and we've sort of organized them in that way. So then we'll say a class H has an infinite Littlestone tree if one can construct an infinite tree of that type, such that for every finite depth path, there's a classifier in the class H that's correct on all the edges along that path. Okay, so there would have to exist some classifier that's labels the root as 1 and labels x1 as 0 and labels x1 0 as 1 to whatever finite depth you want, and that's true for any path. Okay, hopefully that's clear. We will go through some examples to clarify that in a moment, but maybe first I'll state the result. So this is what we can show is any class H is learnable at an exponential rate if and only if it has no infinite Littlestone tree. And otherwise, if it has an infinite Littlestone tree, then it's learnable at a rate no faster than 1 over n. Okay, so that was like one of the bullet points from the trichotomy of optimal rates. So these Littlestone trees completely determine whether the optimal rate is exponential or at best linear. So yeah, maybe I'll go through some examples just so we can see what these Littlestone trees are like. Here's just a simple example where there does exist an infinite Littlestone tree. So these threshold classifiers on the real line. So X is the real line, and these are classifiers that there's some point and everything to the right of it is 1, everything to the left is 0. So these do have an infinite Littlestone tree. And the way to see that is you could just pick any point, and then essentially, I can label that 0 or 1, and then whichever way I labeled it, I just sort of constrain to half of to the half line where, let's say I label it as a 1, then I constrain to everything to the left. And then I can just pick another point. It's essentially sort of a recursive copy, almost a recursive copy of the threshold problem, right? So I can just pick another point over there and split on that, and I can keep recursively splitting, and I always still have some freedom to label as 0 or 1 in whichever side I'm constrained to. And so I can build this infinite tree, just sort of recursively build it. So hopefully that's kind of clear. So since there's an infinite Littlestone tree, threshold classifiers are learnable no faster than a 1 over n rate. And actually, it's not hard to see that it's exactly a 1 over n rate. Another simple example is singletons, and this is one where there is no infinite Littlestone tree. So these are, let's say we're still on the real line, and now, for every point, there's a classifier that just labels that point 1 and everything else 0. So here there's, there can't be an infinite Littlestone tree because, if you pick anything that'll be the root and you branch right, well, I've just labeled that point as a 1, I'm done. Like there's one classifier. So I can't possibly build that tree any deeper to the right. So that's a very simple case where there's no infinite Littlestone tree. And one interesting thing is actually the usual approach to pack learning is the principle of empirical risk minimization, where you just minimize you pick any classifier in the class that's correct on the data. And what's interesting is that some ERM learners will fail here, meaning they'll get a 1 over n rate rather than exponential. So it sort of means you have to be a little bit more careful in designing the learning algorithms if we want to get exponential rates. Okay. Yeah, maybe just a slightly more involved example here, which shows that you can get exponential rates even if you don't have finite VC dimension. So this is saying I can pick any 2 integers, let's say 4 to 5, and then I can put 5 ones between 4 and 5, and then 0 everywhere else. Right. So I can pick any I and put I ones between I minus 1 and I, and 0 everywhere else. So this has an infinite VC dimension, so it's not learnable in the pack model, but we can get an exponential rate because once you pick whatever your root is, you branch right. That is some point in one of these intervals. Let's say I, some I. Now I can branch right at most I minus 1 more times after that, right? So after you branch right I times, if they're distinct points, then you can't label anything else as 1. And you could, of course, if you pick your root further and further out, you get bigger and bigger I, but you'll still always have a finite limit on your depth. So there are arbitrarily large trees or arbitrarily deep trees, but they're all finite depth. There's no infinite tree. So since there's no infinite tree, we get that this class is learnable at an exponential rate.
Hi, Steve. Can I ask a quick question?
Yes.
So is there a notion of a typical tree if, because I mean, so far the tree doesn't take the distribution into account. And so is there a notion of typical tree that might take the distribution into account and where the question is leading? And that could maybe even potentially give a sense of what the constants in the rates might be.
Oh, yeah, no, I in a sort of like a distribution dependent version of this tree idea, yeah, I don't, we certainly haven't considered that much detail. These are, okay, so these trees are the universal rate analog to Littlestone dimension in the uniform rate setting. And there are sort of distribution dependent sort of notions, things like sequential Rademacher complexity that, yeah, maybe could generalize this. We haven't done anything about that yet. Yeah, just done the basic thing with the there exists a tree or not. Hope that answers the question. Did you?
Yes, it does. Yeah.
Okay, cool.
But the question is coming from the fact that in this case here, you have potentially every tree is of arbitrary size, but they are all finite. And so then the question of can one define some notion of typicality? But yeah, thank you.
Oh, I see. Yeah, for this one, yeah. So the for a given distribution, yeah, maybe there would be some kind of yeah, typical depth of the tree that well, for a given distribution, there is a in this particular class, there is an I that corresponds to the optimal function, and probably that would then determine the depth of the tree that determines the constant in the bound. Yeah, so I think you could get a very explicit constant for this particular class using that principle. Yep. Yeah, we haven't explored too much about general ways to derive what those constants are. Cool. All right, so that was the general result and just a few examples. Maybe I'll get into just an outline of how the proof of it works, like the algorithm, and how you can see some of the principles that go into how it all works. So we'll start with some review of some results from infinite game theory, and specifically Gale Stewart games, and then talk about a way to convert that into a result for online learning, which is a sort of a universal rates version of mistake-bound learning that Littlestone studied in the 80s. And then finally put that together with some statistical arguments with data splitting and voting. Some of these we'll do at a higher level than others. Okay, so I'll start with this background in Gale Stewart games. So basically what we're talking about here are games where there are two players, A and B, and they alternate taking turns, and they can observe all the past behaviors, but not the future. So, think about chess or something like that. And then there's a winner that's determined by the infinite playout sequence. And then an important fact that we'll use is that if, let's say, B's winning sequences are always witnessed by some finite prefix, so there's some finite time when B can say, okay, I'm going to win this. Then if that happens, then either A or B has a winning strategy, meaning that they can always win if they play that strategy. And this is I won't get into the full proof here, but there's just a topological argument where A's winning sequences are a closed set. And so you can sort of either keep going back into it, or B can keep you from doing that. Okay. So then what we'll do is define a game. And this is sort of like a little bit like online learning. And so here's the game. So A proposes a point X1, and then B proposes a label Y1. And then A proposes another point, and B proposes another label, and this continues. And the player B wins if there exists some time when there are no classifiers left in the class that are correct on everything so far, right, where all of the xi's are classified as yi. So that's when B wins, and otherwise A wins. So notice that B's winning sequences are definitely witnessed by a finite prefix, because there has to exist a finite time when the consistent classifiers, the set of consistent classifiers is empty. Okay, so we can then use that result from the previous slide. Okay, so then notice that if A has a winning strategy, so like one of the two has a winning strategy because B's playouts are witnessed by finite prefixes. B's wins are witnessed by finite prefixes. So if A has a winning strategy, we can notice that it would generate an infinite Littlestone tree, right? So that would be a case when A has a move such that no matter how B answers, A has another move such that no matter how B answers, and so on. And you will never have emptied this set of consistent classifiers, no matter how B has answered to those previous rounds. So that would just sort of exponentially grow into a tree. And otherwise, so you can sort of say this in the contrapositive. So if there is no infinite Littlestone tree, then B has a winning strategy. Okay, so given, let's now define a function. So given some previous rounds that have generated these xi, yi pairs, let's define this function g sub sm, where sm is the pairs. This is what B would propose if the next point were x. So it's sort of the function that tells us what b would do. Okay, so then notice that no matter what xi sequence we get, there's some finite time when every classifier in H is contradicted by something. So there's some finite time when B has contradicted everything. This is in the case that there's no infinite Littlestone tree. Okay, so what we can do then is convert that into a learning algorithm in the online learning setting that guarantees a finite number of mistakes. Okay, so we observe, what is the online learning setting? We observe in sequence some xi, and then we make a prediction y hat, and then we observe the actual yi, and we want to count how many mistakes we make. So let's define an online learning algorithm, call it A0. It just initializes this set SM to be empty, and then we'll always predict using the opposite of what player B would propose. So then on each round, we predict the opposite of what player B would propose, given this SM set is the playout in the game. And then if it's a mistake, then that means that yi is actually what player B would propose. So let's add it to the set SM. It's so every time we make a mistake, we increment the game by one round. And just by the argument on the previous slide, if it's that will empty the set of consistent classifiers after a finite number of rounds. But if the sequence of XY pairs is realizable, then that'll never happen. So that also means that you'll make only a finite number of mistakes. Right? You can have only a finite number of rounds of that game, and so you'll make a finite number of mistakes. Great. Okay, so that was kind of the online learning version of universal rates, right? We make a finite number of mistakes. It could be unbounded, but it's finite. And then, right, what we were interested in is the IID setting, getting exponential rates there. So notice that it suffices to have that the probability that you have a non-zero error rate goes down exponentially. And then, okay, the natural thing to do would just, let's just try running this A0 algorithm and use its classifier. But it turns out that doesn't necessarily work because we don't have control over the distribution of the last time that it makes a mistake. Like if that has a fat tail, then that might not give you the exponential rate. But we do this kind of data splitting and voting. And essentially what that does is shift the focus from the mean to a quantile of the I hat of that last time that it makes a mistake. Yeah, so that gets a little bit technical. Maybe I won't go through all those details, but it's just some turn-off bound arguments, essentially. A little bit of selection. Yeah, so. And one remark I will make is that this actually will work with any algorithm that guarantees a finite number of mistakes. So if you give me any algorithm that has this guarantee of finite number of mistakes, this will convert it into an algorithm with exponential rates. So that actually gives sort of an alternate way of getting of proving that you can get exponential rates. Just design an algorithm that gets a finite number of mistakes and plug it into this component. Good, so actually I can give like another example. So we had that sort of abstract algorithm that has the game theory motivation, but you can also come up with just like fun geometric examples where you can design your own algorithms that have, sorry, is there a question?
Yeah, can you hear me?
Yes.
On the previous slide, you mentioned this sufficient condition. So if you show that there is an algorithm that makes finitely many mistakes, then you also get the exponential rate. But this is not necessary, is it?
Okay, so they are equivalent in a sense. So if you are getting IID samples, any algorithm that has an exponential rate will make a finite number of mistakes because of Borel-Cantelli argument.
Okay, okay, it's with me. Yeah, thank you.
Yep. Okay, so right, so as I said, you can sort of also propose your own fun geometric examples. So here's just a simple one: is positive half spaces on the cube of natural numbers. So this is some grid of natural numbers in k-dimensional space, and the classifiers, it looks something like this. There's some positive weight linear separator. It turns out this class is learnable at an exponential rate, and I can define an explicit algorithm that achieves the finite number of mistakes. So consider some data set. Let's say the green points are data points labeled 1 and the red points are labeled 0. Then we'll define a learning algorithm that outputs a classifier that's 1 in this sort of shaded region. So let's see, what is that? That's the smallest convex region that contains the positive infinite cubes that have corners at green points. So it's sort of the bottom part of the convex hole, and then it goes off to infinity in the positive directions. So that's so what we can show about this using a little application of the infinite Ramsey theorem is that on any realizable data sequence, this algorithm will only make a finite number of mistakes. Essentially, every time you make a mistake, it has to be on a new point that's green, and it'll add a little notch to the boundary. And you can use this Ramsey argument to say, well, some subsequence of those mistakes, those notches have to sort of stack up in the same direction. And that can only happen a finite number of times. Okay. Okay, so that's the exponential rates.
Here's a question.
Yeah.
Sloan?
Oh, thanks. I was wondering, the classifier that your algorithm chooses here, it does not necessarily belong to the concept class, right?
That's right. That's important, actually.
Is this, yeah, can you, yeah, do you know if that's necessary?
It is necessary, yes. Yeah, so in fact, even in one dimension, it's necessary. So that would be a threshold classifier on the natural numbers. Because what happens is, if let's say that you're only going to get red points, you're only ever going to get negative points or points labeled 0, then you'll output some threshold, and then it will say, no, here's a 0 point that's just beyond your threshold. And so you'll output some other threshold. No, here's another one just beyond your threshold. So it'll still be a realizable data sequence, but you'll just keep making more and more mistakes. And actually, you can convert that into a statistical argument also to show that you can get like 1 over n. You can't get the exponential rates with proper learners. Yeah.
I see, that makes sense. Thanks.
Okay. So yeah, that was the exponential rates portion. I guess there's a little bit of time, and I'll just sort of talk about the complexity structure and maybe a little bit about the algorithm if there's time for the 1 over n. It turns out very much analogous to get the other part of the trichotomy, the other phase transition, or as you want to call it. So, right, so there's also a complexity structure, also a combinatorial structure that determines whether or not you can get a 1 over n rate or arbitrarily slow. And we call this a VCL tree, for a Vapnik-Chervonenkis Littlestone tree. It sort of combines notions of VC dimension and Littlestone dimension from the uniform rates setting in a sort of very interesting way that we find quite fascinating. So I'll again just try to define it using the picture. The idea now is there's a root node that just has a point in it, and I can label it either 0 or 1. Let's say if I label it 1, then there will be two points in the next node. And now there's 4 different ways to label those. So you'll have 4 children labeled with the pair of labeled points. And then those children will each have 3. So at level k, you'll have k points in each node, and then you'll have 2 to the k children. And so if you have a set of points that's organized in this way, and with the edges labeled in this way, we say that a class H has an infinite VCL tree if such a collection of points exists, such that for every finite depth path, again, there's a classifier in the class that is correct on all of the labels on the edges. And that's the whole labeled data set. So it's sort of the union of the labeled data sets along the edges. Okay, so hopefully that's clear from the picture, more so than from the formal definition below, but if you read it carefully, it does correspond to the picture. Okay, so then the theorem that for this point is that any class H is learnable with a rate 1 over n if and only if it has no infinite VCL tree. And otherwise, if it has an infinite VCL tree, then it requires arbitrarily slow rates. So that's the main result for this part, this sort of the second and third bullet points in the transition between the second and third bullet points in the trichotomy. So yeah, maybe again, just to give some example, easy example where there is an infinite VCL tree. Let's say I can label as 1 any countable subset of the real line. Okay, so that's, I can just pick a point and label it 1 or 0, and then pick 2 other points and label them in any of the 2 possible ways. And, you know, I can always find more points to label sort of independently of the ones I've constrained to so far. So this is kind of a very easy case where you have an infinite VCL tree. A case where you don't. All right. So this.
Quick question. Sorry. Here is the countability of. Is the real line important? Like, is it the same thing if you had integers?
Yeah,
like the countable subset of the integers.
Yep, it's the same.
Okay.
Yeah. So actually, what we're saying here is any set that has all finite subsets shattered in the VC sense has an infinite VCL tree. It turns out that's not a necessary condition, and there's an example in the paper that's not true. That you can't shatter there's not an infinite set that you can shatter the finite subsets of, but it's a little bit involved to define it.
Thanks.
Okay, and yeah, just another example where you don't have an infinite VCL tree. This is a lot like the other one that I mentioned earlier, where so here, let's say between 5 and 6, I have some classifier from a class of VC dimension 6, let's say. So this would be unions of 3 intervals in this picture. And so I can pick any integer I, and then I'm outputting some classifier that, let's say, is a union of I over 2 intervals between I minus 1 and I, and is 0 everywhere else. All right, so it's another example because where once I branch right on the root, I've chosen one of these classes that has a finite VC dimension, right? And so I can go to at most that depth I, actually a little bit less than that. Right, so once I choose a root, it's in some I minus 1 to I, and that's the only place I can find points labeled 1 once I've constrained to a right branch. And then the class is defined such that, well, the only classifiers that can label things 1 in that interval are from this class that has a finite VC dimension, so I can only build the tree out to a finite depth once I've branched right. So that has no infinite VCL tree, and that implies that you have a 1 over n rate. Okay, And just to, again, high level of how this algorithm works, it has analogous components to the other one, to the exponential rates, except now instead of talking about a finite number of mistakes, that sort of element of being finished is going to occur in a model selection component. So essentially, we're going to change models and increase the model complexity only a finite number of times before we find a good model, like a model that can get is essentially a realizable case with respect to that model, and it has finite VC dimension in an appropriate sense. And essentially what happens here is we also have this game, but now it's a different game. So A proposes a point X, B proposes a label for it. Now A proposes two points, B proposes two labels. A proposes 3 points, B proposes 3 labels, and so on. And again, B wins if at any point the set of classifiers in H correct everywhere, correct on all the points so far is empty. And otherwise A wins if that never happens. And again, we can tell if B wins after a finite number of rounds. It's witnessed by a finite prefix. So one of them has a winning strategy. If A has a winning strategy, you can use it to build an infinite VCL tree, right? So again, A proposes X1, no matter what B does, A can find some next move. And then no matter which of the 4 options B does on its next round, A can find 3 points to continue the game, and so on. And it'll never empty the class. But okay, so then if there's no infinite VCL tree, then B must have a winning strategy. And then we can use that essentially in a similar way to what we did before. We're going to go through this sequence, this realizable sequence, and we'll take whatever. Okay, so now B is proposing vectors of points, or vectors of labels for any given vector of x's of a given length. And every time we find a sequence of points that the labels B proposes are correct, that's we can advance the game. Okay, so at some point we'll get to a situation when that doesn't happen, right? We can only advance the game a finite number of times, which means that there's some k such that for any k points, the labels that B proposes are forbidden, like you'll never see them. And this is a lot like how VC dimension is defined. So VC dimension is about like being able to classify things in all 2 to the k possible ways. And it's the largest k such that that's true, which means for k plus 1, there's always some forbidden pattern. And so we can use this proposal by G to sort of like the way you would say the VC dimension is k minus 1, right? We'll never see this forbidden pattern. And it turns out that there are learning algorithms that we can use that this is the only property of VC classes they really rely on. Something called the one inclusion graph predictor that's really based on this. And then again, just to get the concentration to work, we have to do this data splitting and voting, but it works out in the right way, and we get the 1/n rate essentially out of this model selection, sort of finding a class that behaves as if it has finite VC dimension, which means we get the 1/n rate that you would get from the PAC model. Okay, so that's the everything. I actually made it to the end. I guess I pruned enough. So this, in summary, right? There's a fundamental trichotomy. Every class is either learnable with optimal rate exponential, or 1/n, or arbitrarily slow, and that those distinctions are characterized by whether or not it has an infinite Littlestone tree, and whether or not it has an infinite VCL tree. Yeah, so some stuff we're speculating about and kind of working on. We think all of this should extend to the agnostic setting. Actually, it seems fairly straightforward. You just sort of replace the 1 over n with a square root. And we actually kind of also think there's maybe a general theory here where you sort of take these Littlestone trees and plug into the nodes these complexity measures from the uniform rates. And it sort of somehow converts the uniform rates into universal rates. So for instance, in active learning, this looks like it goes through pretty straightforwardly by plugging in something called the star number into those nodes. So this is kind of something we're excited about and currently exploring. Okay, thank you.
Well, thanks very much, Steve. So I'm still recording. There, people feel free to unmute yourself and ask any questions. Or I can also end the recording and we can just hang out and ask questions offline, I guess.
Yeah, I'm happy to answer any questions. I see one. Yeah. Please go ahead.
Yeah, so all this was for binary. Does it easily extend to multi-class without any issue, or?
I think, okay, so we can get sufficient conditions for multi-class by, in some sense, reduction to binary. The loss function is still binary, and so in some sense you can still just make these arguments about the loss function. But even for the uniform rates, we don't have a complete characterization of the optimal rates for multi-class. So that's less clear. I guess once those are characterized, I would guess that we could make it work in the universal rates as well. But that's actually seems to be a challenging problem even for uniform rates.
Thanks.
I have a small question about the distribution-dependent constants. Maybe you answered it. I had to step away for a few minutes. Do you have any sense on how exactly they depend on a distribution? I mean, for instance, what kind of properties of P play a role?
I think it really is going to depend on the specific class, and maybe like some distributions will be easier to understand that for than others. Yeah, there was a question Samari asked earlier about the particular class that I had up for as an example, and in that case, I think it was fairly straightforward to describe the constants, just having to do with sort of a model selection. How long is it going to take you to select the right model? Yeah, and I guess that's kind of how these things would happen. And at least in the 1 over n case, there's a model selection aspect that's going to in some way determine the constant. And in the exponential rates, yeah, it'll have something to do with how long before you're finished, how long before you stop making mistakes, and that's going to depend on the distribution in some interesting way. But we haven't done any kind of a general characterization of it or looked at any in detail at any family of problems.
I see. But overall, I mean, these sounds like relatively high-level conditions. I mean, not like a primitive condition you can impose on P, and in terms of like basic properties to be able to say how this constant depends on it.
Yeah, I think it would depend on the specific scenario. There might be a general theory to be worked out, but I don't know what it would look like. Yeah.
All right, thanks.
Okay, so I'll go ahead and take us offline now.